Okay, so we started enzymes in the last lecture, and we're now going to move forward through enzymes to the next part. So we covered the basics of why enzymes are important, moved across into some basic definitions of some of the things to do with enzymes, such as the cofactors, describe the cofactors made of the coenzymes, and the type of catalysis. We moved through a lot of this, and I believe that we got up to here, actually. I think we just finished this one, which I actually discussed already when I talked about bioenergetics. And this was, again, just talking about the equilibrium, how we calculate the delta G from the equilibrium constant, and how we calculate the biochemical delta G. And we can define the biochemical delta G, and then we can do that. That's going to be the biochemical delta G is when we got 1 molar of product, 1 molar of substrate, and we incubate it with the enzyme, leave it until it reaches equilibrium, and we see where it sits at that equilibrium. Kind of like if you've got a pair of scales and you want to see, well, does this pair of scales, if it's biased, does it bias one way or the other? Well, the best way is to put equal weight on each side and then just see where it ends up. And then we can find out what that equilibrium constant is, where it settles to, multiply it by the temperature, the standard temperature and pressure under a biological setting, and that will give you the biochemical delta G. And then we can do that as relative to Q, which is the where the concentration, where the equilibrium lies, or what the concentration of substrate and products, what they are in any one particular moment in time in a biological setting. And so it may be that the biochemical delta G, it may be a positive number. And we know that that means that the reaction is not going to go forward spontaneously. It's going to favor the reactants rather than the products. However, that is under the biochemical settings, and that's not that's not what the normal biological setting is. And so the biological setting may be such that, although it may favor the reactants, in a biological setting, because enzymes are chained together, it may be the next enzyme along may be removing the product, because for the enzyme, the next one along, one enzyme's product is another enzyme's substrate. And so it may be taking that product and turning it into the next product, thus bringing down the concentration of products. And even though it doesn't favor the product, if the concentration drops down low enough by Le Chatelier's principle, it will push it across. We can find out that by what level that needs to drop by factoring in Q, which I did in the lecture before this one. But it's all kind of ties in to do with this, where you can see that as KEQ gets closer to 1 and then exceeds 1, the delta G becomes smaller and then more negative. We covered that last time, and I believe that was the last slide we got to, and I did that in more detail in the previous lecture on bioenergetics. Where we are moving up to is now, this is a last slide just to do with rates. I believe just one slide on rates, and then a few more definitions before we move on to the kinetics, which is my favorite bit. But let's just round off this bit that I didn't quite finish in the last lecture. I believe that this is a small question on the homework, on the Achieve homework as well, will help you with this. This is just some basic rate chemistry from Gen Chem, which I know maybe a couple of years ago, so I'm just going to refresh your memories a little bit. Just to remind you that for a basic unimolecular reaction, where you're just going from substrate to product, or from reactant to product, but because it's an enzyme, we refer to it as substrate to product, we can calculate what is going to be the velocity of the reaction. And the velocity is given by amount per measure of time. Same as what is speed? Speed is distance over time. Velocity is amount over time. It could be amount of substrate used over the time, or amount of product made over time, depends on which one you want to do, and the units of time of whatever makes sense to you, often in seconds. And the velocity in a unimolecular first order reaction is the rate multiplied by the concentration of substrate. And that's just saying that the rate is given by that lowercase k, and the rate is going to be a rate constant. So it's going to be the same for the reaction. But what you're saying is that if you increase the concentration of the substrate, then the velocity is going to increase, which kind of makes sense. If you supply it with more fuel, then it's going to make it go faster. The lowercase k, that doesn't change unless the structure of the protein changes, which is something else. So that is a first order reaction. If you had a second order reaction, that would be if you had perhaps two substrates. And so it would be, it's not shown here, but the velocity will be equal to K multiplied by the concentration of substrate 1 multiplied by the concentration of substrate 2. And so that means that if you had a lot of substrate 1, but not very much of substrate 2, it's not going to make it go very much faster. In fact, if you have a limiting amount of substrate 2, it might even slow it down because you'll be multiplying by a number less than 1. So there's several things to take into consideration between first order and second order reaction. There's going to be important later on, and I just wanted to, this is from a few years ago for some of you, but I just wanted to refresh your memories a little bit so that when I get onto the more advanced material, it's a little bit fresher. Another thing I need to remind you guys of is, I think I've already told you guys in the last section, I talked about the lock and key model versus the induced fit model. Just want to remind you guys again as well that the lock and key model is not awfully accurate. The lock and key model kind of makes the assumption that the substrate for an enzyme is going to be a perfect fit for the enzyme. What we actually find is that it's going to be a moderately good fit, but it's also going to, the protein is going to morph and change shape. And both the protein and the substrate rather can and will morph to change shape in order to fit each other better to make the binding tighter. But we actually find that it doesn't, the tightest binding thing to the protein, to the enzyme, is not always the substrate. In fact, it shouldn't be the substrate. And in the next slide, we'll find out why that is. The substrate actually will bind fairly well, but it won't bind perfectly well. You'd think that it should bind very, very well. It doesn't. It just kind of binds moderately well. We'll get a little bit onto the reason why next. And just to mention as well is that often there's a binding energy, and that is where when the substrate binds, it will displace some water and then form new bonds with the protein. And what we know from, again, basic chemistry is that breaking bonds cost energy, but forming bonds releases energy. And actually the substrate binding to the protein actually releases a small amount of energy, delta GB. It's only a small amount of energy, but it contributes a little bit that can sometimes be helpful for pushing the reaction along a little bit. They're just something to mention. But it's not just, but not all water will be the place. And actually some of the water will actually help the substrate orientate itself into the binding pocket because it will form hydrogen bonds. And sometimes it can be kind of to bridge a gap. Maybe there is a, get my pen. Maybe the binding pocket kind of looks like this, and maybe you have a substrate that comes in like this, and there's an interaction across here that helps it to bind into the pocket. There's a little bit of a gap up here. Sometimes, and oftentimes, water can fill in that gap and can contribute bridging hydrogen bonds. For instance, maybe there's a water molecule right here, and it forms hydrogen bond here, but then forms hydrogen bonds here as well. So water can also sometimes fill in the gaps where substrates bind to the enzyme in order to help the substrate bind to the enzyme more effectively. Now, this is one of my favorite things to describe is that why I mentioned earlier that the substrate will bind to the enzyme well, but not perfectly. And it shouldn't bind perfectly, actually. It would be a bad thing if the substrate bound to the enzyme perfectly. I'll go through. Now, imagine the substrate is a metal rod, and the product is a metal rod snapped in two. and there's a transition state. Remember when I talked about transition states are the routes that is taken in order to get to the product. So it's if I'm starting out here and I want to get to the other side of the campus, I have to follow a route in order to get there. And the same thing, if I've got a metal bar and I want to snap it into two, the route that I take is perhaps to bend that metal bar, and I bend it until it breaks. And the path is the act of bending it until it breaks. Now, if the reaction was not catalyzed, then the energy of the substrate, maybe here, energy needs to be put in order to bend the metal bar. But once you get to a certain point, it will break, and it will break into the product, which is the two halves of the metal bar. Now, what will happen with an enzyme is that it will perhaps make it so that there is less force required in order to bend and break the metal bar. And maybe that's just, for instance, the enzyme is just bending it over my knee in order to make it easier to bend the bar and make it to facilitate it. I think two people are trying to join. There we go. Okay. And so the enzyme is kind of like bending over my knee in order to bend and break the metal bar. Now the thing is that if the enzyme perfectly and the substrate perfectly fit each other, as you can see here, the substrate perfectly fits into the enzyme. Well, there is no room for it to bend, so it actually makes it harder because there needs to be room for the transition state in there, and there's no room for the transition state in there. So actually, binding is going to be pretty easy, but it's already at a super low energy level because it really likes to get in there. Kind of like if you've got your favorite chair at home and you go and sit down with your favorite chair at home, it's going to be harder to get out of that chair. The substrate binds to the enzyme so well that it now goes to a lower energy level, and not only is it doesn't want to move around because it's perfectly comfortable, but also there is no room for it to move around. And so it actually becomes more difficult to catalyze the reaction. The route is more difficult to pass through. And so, in fact, what you find is that in this bottom model here, where the substrate binds to the enzyme fairly well, it'll fit in there nicely, but the enzyme is shaped to fit the transition state. And because it's shaped to complement the transition state, it wants to become the substrate wants to become the transition state. It's kind of like it wants to, if you sit down in the chair and you kind of adjust and move around in the chair to make yourself more comfortable. The shape of the enzyme is that pushes the substrate towards making the shape, towards making the connections and bonds and facilitating the chemical reaction to reach the transition state. And because it wants to reach the transition state, because that will improve binding, it's actually going to lower the amount of energy to get there. The trick is that once it does get to the transition state, you're now at the top of this peak. And so it will just spontaneously break into the two parts. When it breaks into will break into the two parts in this example, but turn into product. And when it turns into product, it is not transition state anymore. And so if the enzyme was perfectly molded to fit the transition state, then the transition state is going to bind really well, but the product is not transition state. And so now the product can just leave. So it's easier now for that product to just come out and leave. So the enzyme binding pocket is perfectly shaped for the transition state in order to push it towards the substrate, towards the transition state, so that it will, because that's the hardest part. Once it hits the transition state, it will spontaneously turn into product. The chemical reaction will proceed, spontaneously turn into product, and then once it spontaneously turns into product, that product will then leave the enzyme. So that's whereas if it was perfectly shaped for the substrate, then there is no push for it to become the product. And if it was shaped for the product, I guess that there would be less of a push for the transition state. Then once it became the product, it wouldn't leave. So what's the form for the transition state? And I think, okay, and I mentioned briefly the binding energy, the delta GB, which is just that when the substrate binds to the enzyme, it will form a small number of weak intermolecular forces that will contribute a small amount of energy. But it's rather a minor point, to be honest. But that is a factor to take into consideration. The main thing, people, you don't want to get bogged down with the delta GB and think that maybe one of the most important factors is that. I think that one of the most important factors is that the enzyme contributes energy. That's more that the enzyme provides an easier route, although it does contribute a little bit of energy too. And I think that's everything to do with the definitions. So that's an awful lot of the definitions. That's the basics really of how and why of enzymes. Now we're going to go into a little bit of defining that mathematically with some enzyme kinetics. So shifting gears a little bit, enzyme kinetics is the study of how the rates and velocities of enzymes occur. How fast does the reaction occur, and studying that. And it's largely used experimentally. We can determine it experimentally in the lab. There's a lot of experiments. There was the golden age of biochemistry in like the 50s, 60s, and 70s, where they just got a bunch of enzymes and put them in the beakers and try to figure out how fast they work. But that becomes really important, like I say, in biology, because you want to know how fast the chemical reactions occur, and also because enzymes and proteins don't work on their own, they work in tandem with other things. And so being able to understand how fast they work and linking it together can help to understand how the chemical reactions in our body work, and also for drug development as well. What and when to inhibit is very important, or inhibit or enhance. So I like to draw it out on a big thing on the board. And I think that what I'm going to do is that I'm going to take away the slides. I'm going to draw it out on the board in long form. And then I'm actually just going to draw out pretty much what is on the slides. And I'll start out, I'll go multicolor too. I don't know what this is. Okay. We'll start out just with a regular graph. Along the x-axis at the bottom, we're just going to have concentration. And there's going to be a few different things on here. So it's concentration of whatever it is we're talking about. We're going to look at 4 different things at once, plot it on this graph. No, sorry, it's going to be the bottom of the axis is time. The y-axis, the x-axis is time. The y-axis is concentration. My bad. Now let's start out with a blue pen. The blue pen, we will call that a product. And at time equals 0. So let's say that it is everything has been dropped together into a beaker, the reactions go forward, but it hasn't started yet. It's just that exact moment in time. Time is 0. What is going to be the concentration of product at time equals 0? 0. What's going to happen to the concentration of the product over time? It's going to go up. Easy, right? That's not too bad. Sorry. There we go. On the other hand, let's go with a nice red. And the red we'll call substrate. That's going to be the concentration of the substrate. At time equals 0, where's going to be the concentration of the substrate? Right. And what's going to happen to the concentration of substrate over time? Decrease. That's it. Until it reaches 0, around that space. Now the next one, let's pick a color. Let's go for a green. And actually let's draw a little dotted line. So I'm going to put a little break in the bar and a double cross. And that just refers to there's a big difference. Okay. And maybe this goes from 1 to 10, but then this picks up again at 10,000 or something like that. So we'll just say that. These numbers are just hand wavy numbers. I'm going to draw a little dotted line across here. This little dotted line I refer to as E tote. And E tote equals total enzyme, and square brackets means concentration. So the total concentration of the enzyme in the reaction. And so there's a lot less enzyme in the reaction than there is substrate and product. It's going to be much lower concentration. You're always going to have much more substrate than you are enzyme. But the total amount of enzyme is simply just made up of how much enzyme is bound to something plus how much enzyme is not bound to something. Exactly the same as the total number of seats in this classroom are equal to the number of occupied seats plus the number of unoccupied seats. And so let's go for, and so it's going to be E tote, and that is equal to, let's do it green, E0, which is the empty enzyme, plus, let's go for, hopefully this purple shows up well, ES, which is enzyme which is bound to substrate. Now, at time equals 0, nothing has reacted yet. So the concentration of E0 is going to be E tote. So here, this refers to at T equals 0, E0 equals E total. They're the same number. That's what that means. The E total and E0 are the same number because effectively E total is a ratio of bounds to unbound. It's a ratio of E0 to ES. And right at the beginning, before everything has happened, it's going to be all unbound. So we can say that they are the same number. So at T equals 0, E0 equals E total. But what's going to happen over time is, of course, that the E0 is going to decrease. The E0 is going to decrease until it is about 0. And it will stay like that to the end. It actually kind of won't, but we'll go into that in a little bit. At the same time, keep this one just in case. In the purple, at time point 0, at time point 0, ES equals 0, because it hasn't bound to anything. It hasn't reacted yet. So it's going to be down here. But what's going to happen over time is that it's going to increase until it gets saturated. And then at this point here, ES is equal to E total at that point right there, because they become the same number. So they're going to be exchanging where over time until it becomes completely saturated, because it needs time to become saturated. It needs time, needs a moment in order to grab onto the substrate and form a complex with it. And we're going to draw another line down at that point right there. When it has become saturated, when the enzyme has become saturated and E tote is equal to ES, E tote is equal to ES, they're the same number because it is all in the ES form. It's kind of like, again, like with this classroom. Before class has started, classroom fullness is going to be, how am I doing this? Before class has started, classroom emptiness is going to be equal to total classroom. Whereas in a full classroom, classroom fullness is going to be equal to total classroom occupancy, because they're going to be the same number. And it's going to be a similar thing. Once you get to, once the enzyme has had some time to bind to its substrate, all of the enzyme is going to be in the ES form. It is going to break down, produce the product, and then release that product, but it so quickly will then bind with more substrate, we can consider it as being in 100% in the ES form. Now, the thing is at this point right here, it's going to be all saturated in the ES form, and the level of it is going to be steady. And so we call this the steady state. The steady state is when the enzyme is completely saturated with a substrate, and it stays steadily saturated in the ES state. Which means that, what do you think that this one might be called? But at the period of time before it's in the steady state. Pre-steady state. This is the pre-steady state. And this is where ES is not equal to ETOS. It's going to be somewhere in between, depending on the point of time. There is also as well, not in biology, but in a research setting, you might get a post-steady state. That's not really important, but I will just mention it in passing. There will be a post-steady state where, as you start to run out of substrate, there's not enough substrate to keep it full, and so it'll just tail off. That's not very important for what we're talking about, but I should mention it just for completeness. But after a certain point, there won't be enough substrate to keep the enzyme occupied to enter into a post steady state. But that's, like I said, it's not super important. Now, the thing with is that we want to measure kinetics in the pre-steady state. We want to measure kinetics in the pre-steady state during this initial burst in activity. Because if you measure it in the steady state, then not only are you, if you measure it in the pre-steady state, then there is no limiting factor. There is available enzyme to bind with substrate if it can, produce product and release it. So if we think about the scheme of E plus S makes ES, will come together to form ES, which will form EP, which will then break down into the E plus P. Thus, you start with enzyme, you form a complex, but you end with enzyme. And what do we say about catalysts? They facilitate chemical reactions, but they themselves do not change. So although in the middle, the enzyme does change because it's bound to something, what you start with and what you end with are the same in the catalytic cycle. You end up with the same enzyme that you started with. But you're going to go through all this scheme. When we measure enzyme kinetics, we want to measure really how fast it takes to go here. We want to measure how long that takes. And that is best done in the pre-steady state, because in the pre-steady state, you have some E. You have some empty enzyme. There is some empty enzyme available. Now, if you measure it in the steady state, then I've got a feeling this orange isn't going to show up very well. If you measure it in the steady state, you're also going to be measuring this extra bit here. And so you're not going to be measuring how fast the enzyme can work. You also got to factor in how fast it can release the product, and then some more substrate can come in and wait for it. So it'll kind of be like saying, if you wanted to measure how fast, let's say, have you guys ever been to a Costco on a Sunday? Mm-hmm. Right, it's a nightmare. It is packed with people, and you're waiting for ages in order to get served at the checkout. And so if you want to measure how fast you can get through the checkout, if you do it from when you join the back of the line, then you're not just measuring how fast you can check out, you're also measuring how fast it takes for you to get your turn to check out. If you want to measure how fast you can check out, you've got to measure it from when you get to the checkout to when you get to the end of the checkout, when you actually get physically and start scanning your items. And so you've got to have an available checkout in order to do that. So you want to be able to measure enzyme kinetics in the pre-steady state because you've got to make sure there is some free enzyme for the to be able to bind with substrate and then catalyze the reaction. If you measure it in the steady state, you're not just measuring how fast it takes to go from start to finish. You're measuring how long it takes for the last one to finish and then your turn to start. You want to measure how long it takes for you to work, not how long the person before you to finish and then you to work. Because in the steady state, you've got to wait for some enzyme to finish what it's doing and then free up, and then the fresh substrate to come in. You want to start from the beginning when there is already some empty enzyme available, and then you know that it's available, so you know that the rate is going to actually be proportional to the rate of the reaction working, not just the rate of availability of enzyme becoming available. So we always measure it in that burst of the pre-steady state. Now, what we can do with that is that we can measure that little burst of activity. And we can measure it either from the rate of products being made or substrate being broken down. It doesn't matter too much. But let's do it from the blue line. And in the initial steady state, we can measure the rate of the reaction. And we can measure at this state, we can measure the product made, which is going to be X over time. And that is going to give you that's going to give you the velocity. That's going to bring us into the next graph, which we're going to plot. So what we can look at there is that if we look at, if we do bring up the second plot, and this time we do time, and the same thing we do concentration, but we do of product. Actually, just the concentration of product. Actually, I'm just going to put it as P square brackets. And if I use a couple of different color pens again, let's go for that orange shows up fairly well. Does the orange show up fairly well? Let's go for an orange, a blue, and a green. Now, what we can do is that we can, I'll do one more as well. Orange, blue, green. What else have I got in here? I've got that purple. I don't know how different the blue and the purple will be. Let's find out. If we were to do the products made over time in the pre-steady state, and if we were to do a reaction at, oh no, this pen's dying a little bit. It's making a horrible sound. At, let's say, a concentration of substrate, let's say 1 millimolar, for example. And then we'll do it again. Concentration of substrate equals 2 millimolar. Concentration of substrate equals 4 millimolar, and we'll do one more. Concentration of substrate equals 10 millimolar, for example. And what we find is that if we look again, in the pre-steady state, we can see that it gets steeper. As you increase the concentration of substrate, as the substrate concentration increases, the amount of product you make over time increases. So as the substrate, let's go here. As the substrate concentration increases, product concentration over time increases. And product concentration over time is velocity. Speed equals distance over time. So the amount of product you make over time is the velocity. So if you increase the concentration of substrate, you're going to increase the velocity of the reaction. Then, and so that's just the slopes here. You can see that it's getting a steeper slope. This one didn't come up so well because it's crammed in there. I wasn't able to get it. Maybe if I like that a little bit, you get the idea. That it's getting steeper. This initial burst in the pre-steady state is getting steeper as I add more product. We then take that and put it onto one more graph. Stick with me just a little bit longer. And if we do that as we plot it as substrate concentration over velocity, and we call that V0, because it's the velocity in the pre-steady state, so we call it initial velocity. V0 equals initial velocity. That means the pre-steady state velocity. If we were to take many of these points, let's say that we did it at lots of different concentrations, and we can see that as we increase the substrate concentration, the velocity increases. The slope gets steeper as S gets steeper. And so what we find is that if you have no substrate, there's no velocity. But if we take these numbers here and plot them on a graph, what we'll find is we might get something that looks kind of like that, which would then look like that. So these numbers here, which is the steepness of the curve, which represents the product made over time, which is the velocity, which is here. The velocity increases as the substrate concentration increases. So the velocity increases as the substrate concentration increases. And what I haven't shown awfully well is that maybe the 10 point is about the same as the 8 point. I just didn't draw that particularly well, but it's going to keep doing that until it gets saturated. And you get this hyperbolic curve like this. And this makes the basis of the Michaelis-Menten equation. This right here, where you have the substrate increases the velocity. When the enzyme becomes completely saturated, you've added so much substrate that it just immediately goes into the steady state, and it gets saturated and works at the steady state velocity. Whatever that velocity is, that's Vmax. That's the maximal velocity. As a few people already heard, you heard of this one before? Yeah. The Vmax. That's the maximal velocity. That's going to be the velocity of the enzyme when it's in the steady state. That's going to be the velocity. Vmax is the velocity. Where is she? Velocity when ES is equal to E tot. Saturated. Maximal. That's what that is right there. We also have a second number. And if we look at the Vmax, if we look at whatever half Vmax is here, and if we look at the substrate concentration required to reach half Vmax, that is a number called Kn, which is the Michaelis constant. And so what we've done here is that we have interconnected substrate concentration, initial velocity, maximal velocity, and this Michaelis constant. We've got these four things, and we've tied them all together. They're all related to each other. And they're all related to each other by this equation. V0 equals Vmax multiplied by substrate concentration divided by Kn plus substrate concentration. And that is the equation of this graph right here. That's the Michaelis-Menten equation. And so if we know some of these, we can work out the others. Now, Kn is actually pretty important. And, I'm going to give you guys like 2 minutes to I'm going to give you guys a couple of minutes to digest that. Actually, that was real quick. I'm going to give you a moment to digest that, and also take any questions. I'm going to move on to why Km is important, and then I'm going to actually bring up the lecture slides. There's another one we're going to define as well, which is Kcat, which is the turnover number. We'll define that one in a moment. I'll have the lecture slides for that one. But does anyone have any questions about this? You guys good? Awesome, good stuff. Okay. So Km. So Km is important. Kn, like I say, is the concentration of substrate required to hit half maximal velocity. And Km is often used to describe the affinity that the enzyme has for its substrate, where actually a lower Km describes that it has a stronger affinity. And the reasoning behind it is that if there is a stronger affinity, then you're saying that less is required for it to reach the half maximal velocity. Because if, let's say, if you've got two substrates, let's say you've got an enzyme such as hexokinase. Hexokinase is, well, does anyone know what hexokinase is and what it does? Glucose to glucose 6-phosphate, yeah. Hexokinase takes glucose plus ATP, and it generates glucose 6-phosphate plus ADP, with a phosphate being transferred across to the glucose. Thus, hexokinase has two substrates. Substrate 1 and substrate 2. And sometimes it might be, but also hexokinase could also work on, very poorly, but it does also work on fructose a little bit. And so if we wanted to find out, well, what does it work on better? Does it prefer glucose? Does it prefer ATP? Does it prefer galactose or fructose or other things? What is its preferred substrate? But if we were to take it, we could actually compare, we could build these plots for two different substrates. And we could, in black, we could have one substrate, maybe in red, we have the other substrate. And the Vmax may be the same. But the other substrate, we look at half Vmax, is here. So it has a lower Km value. And you notice that with this one, it reaches the maximal velocity faster. It's and the rate, less substrate is required to make it go faster. So we're saying that actually the red one is the preferred substrate. It typically will bind better, and it will react faster, and it will have a lower Km value. So a lower Km value is going to correspond to a faster, usually to a faster reaction rate. We take that as being the preferred substrate, which will usually and probably have tighter and better binding. So a low Km value is actually better, because less is required to get the engine going. All right, and I think now we're going to move on to the lecture slides. But again, does anyone have any questions about this? All right, awesome. You guys are doing great. Okay. Like I said, you have you start at the beginning, you have a lot of substrate, not very much product, but the substrate will decrease and the product will increase over time. You have the total concentration of enzyme. I don't like the way that this graph is drawn. I say every time I'm going to change it because I think the ES should be a little bit closer to ET, but imagine that they're a little closer. At the beginning, there's not very much of the ES form because there isn't any ES form because it hasn't had time to bind. But the enzyme will rapidly bind with the substrate to form the ES complex. And the amount of empty enzyme, which they've just done as E, I like to do it as E0 to make it more clear, will decrease. The point at which they cross over and ES becomes saturated, time before that is the pre-steady state, and the time after that is the steady state, because the level of ES is steady. It's completely saturated, and it's just going to be one in, one out. The total occupancy stays the same, because as soon as it empties, it refills again. And so in the steady state, E total is equal to ES plus E0, and in the steady state, E total is equal to ES. Whereas in the pre-steady state, it's going to be a ratio somewhere in between. If we were to look at the amount of products made over time at different concentrations of substrate, we'll see that it will, as you increase the concentration of substrate, the initial velocity, the steepness, initial velocity will increase. And so if we were to plot that onto a graph, we can see that as you increase the substrate velocity, the substrate concentration, the enzyme velocity increases. The maximal speed, again, I think these lines should be closer together, but I don't like the way that they've drawn this graph. One day I will change it. Is the maximal speed when it becomes saturated, when it hits the steady state. That is the Vmax, and it's going to be in concentration over time. Don't forget your units. It's going to be concentration over velocity is concentration over time. It's amount over time. And the Km is the half Vmax, the concentration required to hit half Vmax. I think I may have, no, I don't. Oh, I do, but that's coming up a bit later. So this is kind of setting things up a little bit. This is just to mention, okay, well sorry, that's so just double check. You guys are comfortable with this so far? I will move. How are we doing for time? Damn. There's the slides 27 of 72. We're almost halfway through. It's cruel, I know. I think we've got this lecture, and then do we have one or two more lectures before the exam? 2 lectures before the exam. So after this, so we've got Thursday, and then Tuesday, and then the exams on the Thursday again. Mm-hmm. Fantastic. I've scheduled the undergrad exam and the grad exam on the same day. Mm-hmm. That was yeah, I'm going to be spending the whole weekend grading. And I'm looking forward to that. Whose idea was that? Okay. So I guess it means I don't have to lecture that day. I'm just going to spend the whole time just like sat while other people stress and work. So. Okay. So okay. So I go up to here. So like I said, we have the reaction, and the reaction is the enzyme and the substrate coming together, and then reacting, and then breaking apart into product. And we draw that as the last one as a forward arrow because the product's probably not going to come and bind with the enzyme again. Technically it could, but we can largely consider that it doesn't. But each of these have got a constant associated with them. And you've got a rate associated with them. You've got the rate that the first step happens. You've got the rate that the second step happens. And the rate that the third step happens. K1, K2, K3. You've also got that, because these are reversible reactions, You also got the rate that it can break apart as well. But generally, it's going to be going forwards, and so K1 is going to be greater than K minus 1. These are little k's as well for rate, I should mention. Now, under steady state, like I say, the ES is constant. As soon as it's broken, the rate of breakdown and formation are equal. And it forms by this K1. Remember, for second order rate kinetics, the velocity is equal to the rate multiplied by the concentration of one, multiplied by the concentration of the other. And so that's it. It comes together by, let me erase everything and start again. It comes together by moving in this direction to come together. However, it breaks apart. It's got two ways it can break apart. It can break apart by moving to the next step, or it can break apart by going back a step. And so the breakdown is going to be the rate of it breaking apart plus the rate of it coming together, moving on to the next step, multiplied by how much of the stuff that you've got. Again, it's just regular rate kinetics, where it's just the first order reaction because there is only one molecule and it can go in either direction. But generally, K2 is going to be the one that predominates. But just to be clear, so in steady state, it's going to come together and break apart as fast as it's going to be an equal amount. It's going to move on to the next step as fast as it can replenish itself. But early in the reaction, remember with Le Chatelier's principle and the way that it's going to move things, according to the equilibrium probably favors moving over to the right. But right at the beginning, so let me get my pen. Let's just make it really abbreviated and just do enzyme plus substrate to make enzyme plus products. And we're just going to skip the middle steps just for this. Now, at the beginning, and it's going to be, it wants to move in this direction. But at the beginning, you haven't got any product yet. You haven't had any chance to make it, which means by Le Chatelier's principle, it's going to want to move over there even more. So the rate, so it's going to, a lot of these middle steps, although they can technically go backwards, because you haven't got any products, and because it wants to make product, it's going to doubly so, more so, want to move over to the right. And thus we can actually kind of ignore a lot of these. We can actually kind of break it down into we can skip a lot of the middle steps, because a lot of the middle steps aren't going to go backwards, because the reaction wants to go forward so much because you haven't got any product. And so it's going to want to move in this direction, and because you haven't got any product, it's really going to want to move in that direction. So ultimately, actually, when we measure rate kinetics, we don't really have to worry very much about the backwards reaction. We just need to worry about K1 and K2. And when we do the pre-steady state kinetics and work out the velocity of the enzyme, we work out all those Michaelis-Menten things. Effectively, what we're looking at is just K1 and K2. We can largely ignore the other things because Le Chatelier's principle is pushing the reaction so far across to the right. So that's just an important consideration to make. Whereas in the steady state, that's not going to be a consideration. In the steady state, because you have a reasonable amount of product that has been made, there's not so much of a kind of desperation, as it were, in order to move over to the right, because you already have some product. The reaction desperately wants to move to the right because there is no product in the pre-steady state. But in the steady state, you've got some products, so there isn't that urgency. So you have to factor in more things. But in the pre-steady state, you don't need to factor in so many things because the reaction really readily wants to move over to the right and proceed forwards. Now we can simplify this actually very easily, and that we can say that in fact, the reaction wants to go over to the right so fast that we can actually kind of ignore this and simplify the reaction to just being this. Because because in the pre-steady state, again, an equilibrium constant, equilibriums, we got the E plus S to form ES. In the pre-steady state, you don't have a ton of ES. That's the point of it. In the steady state, you've got a bunch of ES. In the pre-steady state, you don't have a bunch of ES, which means that it's going to, Le Chatelier's principle is going to move over to the right. Because of that, we can actually kind of ignore that part and just consider it actually as being the concentration of ES multiplied by K2 is equal to the velocity. So in the pre-steady state, we can consider the velocity as being equal to the rate multiplied by the concentration of ES. This is where I start to lose people a little bit because we're drifting into the deeper parts of enzyme kinetics now at this point. We've gone past the stuff you may have done before, and we're probably into some new territory or some old territory a little bit. But largely what I'm saying, if I was to boil it down, is that early on in the pre-steady state, we can ignore a lot of the parts of the reaction. All of this stuff I mentioned at the beginning, in the middle, that's up here, we can ignore a whole bunch of these in the pre-steady state, because you don't have very much of this. It's going to want to move over there. And so we can actually ignore a whole bunch of this. And really just look at it as that. You can ignore a whole bunch of stuff in the pre-steady state because there's not so many limiting factors. And so we can just look at it as just being remember, each equilibrium has got a constant and a rate. And so we can just break it down to just being this. And thus, it's just going to be the velocity is equal to the concentration of ES multiplied by K, in this case K2, because it's the second part of the reaction. That's going to be the initial velocity. I remember from the rate kinetics, I said this is old stuff from a little while ago, and I did the velocity is equal to K multiplied by S. I showed that like right at the beginning of the lecture. It's just that. It's the same thing. The concentration of the enzyme substrate complex multiplied by the rate equals the velocity. Now, how this relates, how this kind of ties together again. How long have I got? We've got just under 10 minutes. We've got like 8 minutes. So I'm going to tie this up and then leave it there. It's a nice way to tie it up. Now, in the steady state, you're going to remember. In steady state, we're going to hit Vmax. You guys comfortable with that so far? That was what was on the graph before. In a steady state, you're going to hit Vmax. So steady state hit Vmax. Why are you going to hit Vmax in the steady state? What is it? What is it about? What is present that is going to allow it to hit Vmax when it's in the steady state? What is it about the enzyme? Where in this saturated, right? Saturated. Because brutalize that, didn't I? Because ES is equal to E total, saturated. Okay. That means that in the velocity equal to ES, let me do it the original way to keep it equal to K2 until it's getting late in the day, multiplied by the concentration of ES that we did before. Well, that means that if that's how it is normally, we substitute that in, and we'll draw this, write the same thing again. V0 equals K2 multiplied by ES. If we make it so it's in the steady state, when ES is equal to E total, so that's going to be when it's during the steady state, when ES is equal to E total, then that's not going to be V max, V0, it's going to be V max. So V max is the maximal rate of reaction when we have the total concentration of the enzyme multiplied by the rate, because that is going to describe how fast it's going to be when it's completely saturated. When it's completely saturated, that's when you hit V max. So that kind of ties it together. The initial velocity is going to be the rate multiplied by however much ES you've got, and the V max is going to be whatever the maximal possible rate is going to be. But I think to finish that off, I'm going to skip forward a couple of slides to this slide here. Well, let me just stop. Are you guys comfortable with that I've written out? Mm-hmm. That you're going to, when ES is equal to E total, then V0 is going to be V max, because this is always true. And if ES is equal to E total, then that's when you're at the steady state where it's completely saturated. And we know that when it's saturated in a steady state, that's when we hit V max. So velocity V, I guess it could be that it's still V, but then V equals V max. You could have it so it's like this, but in this case, V is equal to V max. Does that make it a little bit clearer? Under velocity, under these conditions, is V max. That's just it. I guess I kind of skipped that kind of bit in between, but that's essentially it. Now that is going to be, like I say, dependent on the concentration of ES, which again is going to be, that's for a chemical reaction that occurs where you've got a bunch of enzyme and a bunch of substrate. But we could also work backwards a little bit and work out what K is. And so remember, that's the rate. And so if we actually just rearrange that equation, and instead, if we just do it as V divided by ES, that will give you the K2. That will give you the rate. So we can just rearrange it. So if we're able to find out whatever is the velocity at any one particular concentration of ES, then that is going to give you the rate, the K2. And the easiest way of doing it is actually to just do V max divided by the concentration of total enzyme. That's going to be the easiest way of figuring out what is K2. And K2 is often, but not always, and if we were doing like an enzyme specialist course, then we would talk in a little bit more detail, but 99 times out of 100, K2 is also referred to as a term called K-cat. K-cat, which is the turnover number, which is here. If V max is equal to K2 divided by E total, then V max divided by E total equals K cat, and K cat and K2 are generally considered to be the same thing. There are some cases where they are not for specialist reactions, but generally we just refer to K2 as being the Kcat, which we call the max rate of reaction equals what? Max rate of reaction. Yes, the max rate of reaction, so the Kcat is the max velocity of the reaction divided by the enzyme. And that gives us the Kcat, which is referred to as the turnover number. That's the number of substrate molecules which can be converted into a product in a given unit of time, which is usually seconds. So the Kcat is the number of molecules that can be turned into product in 1 second. So this enzyme catalase can turn 40 million molecules of hydrogen peroxide into water per second. And that's an extremely efficient enzyme. Whereas, let's say, fumarase can turn 800 molecules of fumarate into malate per second. So it's just a different measurement of saying things. How many molecules can be turned into products per second? Is the K is, and we can calculate Kcat as just being Vmax divided by E total. There will be questions in the exam on all of this stuff. There will be questions in the exam saying calculate Kcat.